right. Can you hear me okay? Yeah, also in the back? All right, great. So, whilst the final people are entering, it's great to see a nearly full room this morning so early. So well done to all of you. So my name is Justin van der Hooft, and together with Esteban, Rosina, and Jonas, we prepared this workshop for you, or actually mainly they did it. And it's my pleasure to welcome you. So first of all, a few announcements. So on your desk, there's a note for the Wi-Fi for the workshop. We highly recommend to connect your laptop to that Wi-Fi so that you have a more powerful connection if you want to download some of the stuff that we will be working with. Yeah. So another announcement is that we will take some pictures during the workshop. If you really don't want to be on any of these pictures, don't hesitate to tell me, and then I will make sure that those pictures will never see the daylight. Then, the program of the day is that I will say a few more words about MS2LDA and its position in the landscape of metabolomics. Then we have Esteban, who will show you the power of MS2LDA in natural product discovery and how it can help to structure annotate fungal metabolites. And then we will move on with MS2LDA version 2 tool, what it is, how we can use it, and you will also get a chance to play with it. So this is an overview of, I would say, typical, or maybe for you atypical, untargeted metabolomics workflow, where we also highlight where the role of topic modeling, which is what MS2LDA is doing, can be in the unsupervised discovery of scaffolds and substructures. So basically, if we start with, in this case, natural product samples, but this could also be your urine or plasma samples or whatever you measure, you end up with a lot of spectra. And if we consider all the peaks you get as pieces of the puzzle, then topic modeling can help to kind of find how these pieces fit together in a little bit larger blobs to make the final puzzle to get to your metabolite structure more easy. And in the end, and that's also what we're working on together with Jonas and Rosina, to help you to also connect even functions to your molecules. So they gave me like 2 minutes, which I think are over now. So it's my pleasure to give the floor to Esteban, who will now show you a demo case of MS2LDA.
Let me put first a slide. But for me, it's a pleasure to be here. And actually, let me just, no. So for me, it's a pleasure to be here today. And actually, I'm very honored to share with you what has been for me a very interesting project, because for me it was one of the first projects that got me into untargeted metabolomics and in-depth metabolomics. And it's a very beautiful project, actually, because it's from a fungus that we discovered from Cali, my original city. And so basically the title is like Metabolomics Insights into the Polychaetae lactones from the Porticaliensis, a novel species. And basically, why do we study fungi? And basically it's because these microorganisms can be our allies in many different roles, and actually they can be friends for us as the roles in preserving ecosystems. They can be alternative sources of food. Actually, they can also be useful for production of alternative fossil fuels, and also bioremediation. And in our case, in my previous research group in Germany, we were actually interested in finding new antibiotics. And why is that? And it's because basically there is what we call antimicrobial resistance, and it's that many of these microbes that sometimes have generate many diseases, and sometimes you get sick and you get administered some antibiotics. Sometimes these antibiotics, they don't work, and it's because these microbes are resistant to them. So basically, they have been directly related to more than 1 million deaths per year, by 2019, but already they are indirectly affecting more than 5 million deaths per year. So that's significant numbers. And on this search of new antibiotics, we wanted to focus on Colombian fungi. And why those? And actually, Colombia is one of the biodiversity hotspots in the world. And despite the fungal community in Colombia has been lacking many advances because the infrastructure in academia in Colombia is not as good, probably, as it's been here in Europe, and the technology developments are always a little bit behind. But we have been trying to push this forward, and for this, we actually tried first to start looking into the diversity and this untapped potential that they have. So we started by looking at this beautiful fungi from Colombia, and in my previous research group, we actually had a look at these fungi that they are endophytes, and that they are endophytes. It means that they live inside the plant's tissues without causing any symptoms in them. And actually, we were looking at endophytes of medicinal plants. So plants which have been used in tribes in Colombia for medicinal purposes. And by doing this, during my PhD, we found a fungus which was the first novel species of Cali and was isolated from the medicinal plant Otoba gracilipes. So we actually named it the Aporte caliensis for Cali, and we were also intrigued on their chemistry because basically we wanted to explore the hypothesis that if these plants have some medicinal properties and these microbes live inside them, they might also have some very nice properties that we can explore. So basically, in a normal chemistry lab, we want to isolate the major metabolites from this is the LC chromatogram of its culture in vitro, and we actually were able to replicate the ones with the smallest starts, but we isolated the main peaks, which is 1, 2, 1, 3, and then at that time, I tried to see if I will use on feature-based molecular networking, if these compounds will come together. And we see that 1 and 3, they come together. So we were actually wondering, are they related or not? So we actually see that after NMR structure elucidation, here you can see that 1, 2, and 3 are the compounds in this feature-based molecular network constructed using cosine score. And we see that 1 and 3 are not related so much. And then we were actually intrigued by this. Why this happening? Why the feature-based molecular networking gave us this result? And then we started evaluating the topology of these feature-based molecular networks, and then we see that if we start increasing or decreasing the scores, in some point, like compound 3 is appearing as a singleton, so it's not anymore clustered together with the other compounds. And we then had a look at the fragmentation patterns, and we see that FOMOL, the compound on the left, has patterns that are associated to the 10-membered macrolide lactone, while the small butenolides, which we call calienzolides also for Cali, they actually share a lot of fragments and losses. So then we went to use MS2LDA, and actually here you can see a very interesting pattern, and is that actually MS2LDA resolves the MSMS is a fragmentation similarity between the 2 and 3 compounds, which are sharing the same mass to motif. And FOMOL has a motif which is only shared by it. But we can see that there is in between a lot of chemistry, which seems to be much more complex and sharing many motifs in common. And maybe this is the answer to why these compounds were clustered together in our feature-based molecular network. So there is a hidden complexity in the chemistry of these polyketide lactones that was only uncovered by MS2LDA, by linking this spectra to the motifs that they share. So basically, if you're interested in actually seeing more about this work, you can see our paper, which was published some years ago already. And basically, with this, I want to tell you that our results contribute to saying that we can actually translate taxonomical novelty to interesting chemistry, and also that for us, natural product chemists, relying on automated, untargeted analysis sometimes might be misleading, but this only needs to, or leads us to actually try to use other tools to complement our analysis and do more in-depth investigation. And for this, MS2LDA 2 now is very interesting for us, and we are very excited to see these new developments. With this, I would like to thank you all for your attention and all my collaboration partners from my previous groups in Germany and Colombia, and my actual group now in Wageningen, where actually it's for me a very nice thing to say that I came to this group thanks to a conference like this. So thank you very much. So now I leave you with Rosina.
Hi, yeah, I'm Rosina, and I will continue. Going back to or going to the hands-on. But first, what is the principle of MS2LDA? We have the principle that same fragments and losses, as Esteban mentioned, represent or may represent the same substructure. So, for example, we have two different spectra and two different structures, and we can see that they align. And as well, some fragments or losses can also be shared between different spectra. So this is if you need to relate a concept of MS2LDA, please, if I want you to stay with a concept in this workshop, it would be this one. But what is behind this? No? What is the algorithm that works on MS2LDA? And this is topic modeling. So this was developed some time ago, actually. It is not new, but it helps us to find patterns. So we have two texts. One is for tennis and one is for running. But they share some words that can be related to sports, for example. So in this way, we can apply this for spectra, and we can say that some structures share these substructures, right? So we treat the spectra as documents the same way as we do in these two texts, basically. So what is the output of MS2LDA, right? What exactly you get? You get a mass-to-motive, that is this combination of fragments and losses. And what is new, this was an algorithm and a tool that was developed by Justin from a long time ago, but we have a new version, so we want to present this new version, the MS2LDA 2. But what is new? First, we improved the speed a lot. So before, it was run through GNPS. If you already kind of know more about MS2LDA, it was run by GNPS, but also through a server. However, for large data sets, or not very large, but kind of large, it was almost impossible to run. So now we increase a lot the speed, which allows you to also analyze large data sets that sometimes other tools take really a while. So the second major, or one of the most major improvements, is the mass-to-motive annotation guidance, because before you needed to do it by yourself. I will explain a little bit more later, but this is a very major feature, new feature. And finally, the integration, because now we have so many different tools. Sometimes it's a little bit overwhelming, I guess, also for you. So which tool to use, right? So now we try to integrate other tools on top of MS2LDA, building, for example, on MatchMS, or even MySQL to find, to mine these patterns that we infer with MS2LDA. So a central concept or feature that is introduced now that, in this new version is MAG, and MAG is the mass-to-motive annotation guidance. So before, when Justin and other collaborators published the paper of MS2LDA, the original version, you still needed to, I don't know how many of you are familiar with MS2LDA. Can I ask you that? How many people were? Okay, yeah, some people were. Yeah, some people know already what I mean. But yeah, so once you had the mass-to-motives inferred by MS2LDA, you still needed to do as a chemist or as a PhD student maybe, infer what was this motif related to the substructure. Like you at the end needed to still annotate the motif. And this is also what Esteban did when he published his paper. But now we have this new feature, and this is that we trained a library, and we have some recommendations of structural recommendations, what we call structural recommendations, and these are given by this new version. Although at the end, you still need to understand what is the thing that they share in common, because at the end is what is the hit of the MAS2 motif. So yeah, this is one of the major features of this new version, and I hope you can try it, because this also allows you to apply MS2LDA without, no, I'm not saying that you shouldn't have some chemist knowledge about the structures or substructures that you are looking for, but still it already gives you some recommendations, and from that you need to work on, right? So yeah, let's do something. So
Thanks, Rosina. I'm Jonas. I'm also a PhD student in Justin's group, and I will guide you now through the workshop. Let's start with how you could use MS2LDA, and there are basically three options. There's the beginner one, so if you have no experience at all with Python, then you can use a server. The second and third option are really similar, and today we will only focus on the second one, and that's also the first part, what we are going to do. By far the most challenging thing to get software running in general. So we will spend now a fair amount, maybe 15-20 minutes, on trying to install MS2LDA on your laptops. Can I see a number of hands who has Python and Conda installed on their laptops? Okay, that's most of it, or a little bit more than half, that's fine. Everyone else, so if you have someone close by who has Python installed on the laptop, maybe group together. That would be nice. A few can try to use the server, but no promises. The server is really weak, so it can crash, then let us know. And I have one spare laptop I can give to a group who says like installation not gonna happen today, so I can give that as well. If you have Python on your laptop, then the first thing to do is please go to this GitHub repository. Yes?
These slides, can we download them somewhere?
We can share them afterwards.
Ah, okay.
But
It'd be nice to copy paste the links.
ah, yeah, that's true. That's a fair point. Okay. Is there a group who says like, I would like to have your private laptop? Is it because of me or?
If someone wants to sit with me and find
Okay. I think maybe we will walk around and help you with that. I stopped the time. If you manage to type in the link, then you can scroll a little bit further down below. I wait for that a little bit. And there's an installation guidance, and that will help you.
I think also if you Google GitHub MS2LDA 2, maybe it also appears. And it's easier than. Yeah.
So if you all typed in the GitHub link, then you scroll down, as I said, there's an installation guide for Conda. You click on this link, and then you follow step 2 and 3. Right, just to do it again, you're on the GitHub repository webpage, on the start page. You scroll down, there's a Conda installation guidance, and do step 2 and 3. If you are at home or so and you don't have, for example, Conda installed or Python, you can use the first step as well, but I think for the workshop that would take a little bit too much time, so that's it. Okay, hello. Can I see some hands for whom is this already working? None. Okay, one. Yeah, no one was raising their hand. Can I see it again? For whom is it already working? It's also fine if you use the server, for example. This is also working. Is it working for you? Okay. Okay. We wait 5 more minutes, 7 more minutes, and then we start with the action. All right. Okay, I think we tried it at least, so happens. I think the bandwidth of the internet is not working for at least most of the people. So what we will do now is, let me skip a little bit ahead. We actually have to download something else, but that's maybe a little bit easier. And this is actually the data set we want to use today, right? So go to Zenodo. I tried, you can also just type in MS2LDA Zenodo if you don't want to copy the link. Then you will come to the Zenodo web page and download the case study results pesticide 250 MS2LDA with. You can also download it if the installation process didn't work, because we will now mostly rely on the server. The ones who have my laptop, you don't need to download anything. It's already on the laptop, the file. So this is the next step. On the side, you can't see it on the slides here, but it's version 7 that is the most updated on the Zenodo. It's on the right-hand side. And then just this case study. Any other version with this case study would also work. That's not a problem. I would say maybe 5 more minutes and then we move on. All right, I think it's time to move on. Because I think it's quite difficult to read from the back, I will just show you once more how to download the file if you haven't done yet. So what you're doing is, you just go to Google, write MS2LDA, and then... Oh, yeah, sorry, thanks. MS2LDA.zenodo, I can't read it. Then the first thing you can see is from the Hooft group, MS2LDA. Version 7, it's important. You scroll down, and then you just download this file to make it really big. Case study, pesticides 250, and here's the download button. Okay. But yeah. One thing I actually wanted to avoid during this workshop is to recommend to you to go to the server, but I do it now because I see it's really not working with the installation with the Wi-Fi. So we try to use the server until the server crashes. You can go to the website, it's just called ms2lda.org, and then you see a green button in the middle below the picture, which says try the new ms2lda.viz visualization app. Click on that, and then, yeah, I mean, if you're not already grouped, right, especially for the server, because it can crash, would be good if at least 2 people would group up, yeah, to have small groups. Okay. So I wanted to say something about the dataset we are going to use today. And compared to the datasets Esteban described, it's a rather simple dataset. So I'm working in the food safety area, and what I did for a case study, it's also in the bioarchive manuscript, is I had some blank tomato samples, and I spiked this tomato samples with a list of 211 pesticides. A few things maybe about the data set. So it's roughly 10,000 spectra, and because it's a really important parameter, we selected 250 master motifs, which kind of says, okay, we want to have 250 substructures modeled. It's not 250 substructures. You will see that in a second as well. All right. And obviously the goal of this case study was that we want to find now substructures that are related to common pesticides. So I jump now again over the dataset, over downloading. Before we do our first exercise, I want to show you what you can do if you have the desktop app running. It's not possible on a server. If you have the desktop app, the visualization app running, you can also actually do your own analysis there. And there's then a run analysis tab on the most left side. A really important parameter, as I said, is the number of master motifs. So the estimated substructures. If you have a data set, think about a number of substructures you would expect and add a bunch of them. It's also good to just try it out, right? If you think, okay, maybe 200, it's a wild guess, and you see, okay, the results are not as expected, go up. Go to 250, go to 300. And maybe you can use all the information you collected over the time. Then, really important for the new annotation feature is that you download some Spectra files. Just need to press a button actually here. And then the advanced settings, we will work in the next month on the documentation that will explain all of this. For now, you have to trust me, the advanced settings are fine as they are. If you're not really looking for something really specific, and then you can just run the analysis on the bottom. Okay, then let's do something. I hope you can all see the load results webpage, or at least most of you.
Maybe, can you confirm?
Yeah, said. No, I think there are a few more. Yeah, I've probably not working for everyone. But that we show some use cases, I would move on. And the first thing you do is you either drag and drop your file onto this list. It looks maybe a little bit, no, you're on the server, so that's fine. Or click the button, the file you just downloaded, you can use the JSON or the zip file, upload it, and then you have to press again the load results button. And what you should see if that was successful is you have like green confirmation that the selected file was successfully uploaded. If this happened to you, I will have a walk around. Yeah? Question or? I will have a quick walk to see how the server is doing, and then I'm back. Okay, it seemed to work for some it worked on the server so far, for some not. If it happens to work on your server, then the next thing you would do normally, if you have done your analysis, is you want now to explore what you actually found in your dataset. And therefore, you click on the motif ranking tab. This will now be on the server, right? Also take some time. But I will go with you through what you can actually see on this tab. So in general, the motif ranking is basically the more or less the main page for the overview. And what I did straight away is, to simplify it, I searched for one motif, and I know that this master motif is a good one. Just that we can have a look at all the properties of this master motif. I'm now a little bit wondering if you can see in the back actually the bottom row. I hope so. So we're not running any. Yes, they are below the motif header. You can type in any number. So the easiest would be, if you just want to follow, just type in 236. But I will explain now a little bit more what you can see in this table. So the first one is the degree. What is the degree? And it says 37. The degree says that out of those nearly 10,000 spectra, 37 spectra have the highest association with this specific master motif. So that could be an indication maybe all those spectra have a structure that is related to the master motif 236. After that, there is an average probability score. This is basically a score that is generated by the topic modeling algorithm that tries to associate, okay, how well is every spectra out of those 37 actually associated with the master motif, and the scores between 0 and 1. And you can see for this motif it's 0.58. On the top there's a slider, so you can also adjust the thresholds if you have, I don't know, like 1,000 master motifs generated and you only want to look at a few of them. You can set with the slider threshold. I would encourage you to not go too low because you can see already, I know this is a good motif with an average score of 0.58. Even more so with the average overlap score. The average overlap score describes if you compare the fragments and losses of the master motif with all the spectra, all the 37 spectra, how high is the overlap. And here it's even lower, but you can certainly set a threshold there as well, maybe to 0.1.
What do you consider good probability and overlap score?
Yeah, so this is a good question. It's a little bit more difficult than this.
Repeat the question.
Yes. I can repeat the question. So the question was, what is a good average overlap score, maybe also probability score to look out for? As I said, this can be a more difficult question because the degree, it all depends here on the degree, and the degree just says, okay, this spectrum fits the best into the master motif, but it doesn't say it fits well. It just doesn't fit in any other master motif as well. So, and it can be that, for example, in this case, an average overlap score of 0.27 is really good because maybe there are 5 spectra who are best related to this master motif, but not really good. So I would say for both, maybe set to 0.1. If you have not too many master motifs, it's, if you don't use the server, it's quick actually. So just click through the master motifs. It's really easy to explore if you have probably a good substructure or not. The new feature, this is all you could actually see with the old MS2LDA.org as well. What is new is this annotation side. So there are a lot of smiles that come from the structure recommendations from the new tool. And also something new is that you can query now for master motifs. And maybe you're familiar with MassQL. MassQL is a query language which allows you to look out in a big collection of mass spectra for combinations of fragments and losses. And you can just type in any query you want, and that will filter for you master motifs. I will show something later as well. Okay. Maybe now you see this table and think like, hey, what should I do with it? What I do normally, what is the first step, is I just have a look. I click on the link. You can also do that if everything loaded. So until now, on the motif 236 or whatever motif you're interested in, then you still will need some time on the server. And what happens is you get redirected to the motif details tab. And there you see now, the first thing you see are the structures recommended by MS2LDA 2.0. So those are all the structures. And what Rosina earlier explained, how do you interpret that? So what we would do now is that we have a look at all the structures and look what do they have in common. And then you can maybe see it's this dimethoxylated ring system up to the sulfur group that is in common for or shared by all of those structural recommendations, and that is probably already a really good lead what a substructure is represented by. How is it going on the server? I don't want to ask actually. Okay, it's hanging.
It's not crashing, but it's hanging.
Okay, that's good, I guess. Yeah. Okay. Yeah, I mean, if you really want to use it, I can really recommend spending some time for the installation, not with this bandwidth, but maybe later. We are obviously here at the conference during the entire time, so we can have a chat about it if you want to have any hints or whatsoever. You have the data set, I hope. If not, then ask us, we can share it again and then explore it. Yeah. Okay, I think normally we would now do a task because I tend to talk always quite a bit, but with the server problem, I'm not sure. Maybe I will do it myself and show you how it will look like, and then you can maybe retry it if you're interested, and I will share the slides afterwards, and then that's fine. The first task I actually wanted to ask you, actually my laptop can do that, that's perfect, so we have one really encouraged group, is that I know that those are pesticides that were spiked into the tomato sample, and here I also copied the spectra from Mass Bank, probably also difficult to read from the back actually. And now the goal would be, can you find master motifs related to those structures? I give the one group a little bit of time, but maybe I can do it like this. It's a little bit small actually, yeah. Okay, because it's just one group, I will do it by myself. So I have here the dashboard running. So, but I'm not sure. I think, yeah, I loaded the file already, right? So that's done. I go to the motif rankings. That was not on purpose. Yeah, so then we type in the query, for example, which is query. So this it's difficult to read. Okay. Student data. MS2LDA. So this will now be a little bit of jumping, but the easiest way to do, let's say you suspect to have this structure in your data set, right? And you want to see, do I have a substructure that's related to this structure? Then the easiest way is always to check, okay, what are really, really dominant fragments in the spectra, and just search for them. So let me go here. This is that typed correctly? Should be correct. So then let's just type 70.04. This is like the biggest fragment here. One query, we get one master motif, right? So, and then, as I said, the easiest way to explore it, just click on it. And hello. Okay, it doesn't want actually. Okay, but you can see it's, let me try that, it's motif 98. Let me check, we can also sort them because for some reason that won't. And yeah, here you can simply explore then all the master motifs, right? Okay, I will show you something about that later, but let's go maybe to the next one. This one is the benzoyl-urea structure, and here we do exactly the same, right? We try to find it by where we scan. Oh yeah, that's better. Yeah, it's always switching between German and English keyboards. And here, I think there are two really dominant fragments. One is 141 and one is 158. So we can try that out. One the query. Yeah, so normally so the question was how to know which MZ value to pick. I mean, obviously I know what I'm looking for, so for me it's quite easy. But normally I would aim for the fragments of the highest intensity. Check them first. If you find something there, that's a good indication. Because also in the model, we kind of include the intensity in the modeling, so they have also high probability to end up in a substructure actually. Aha, wow, it works. That's good. So now what I did, I can go back if you want. So here I get two structure recommendations for the MZ value 141. And then I just click on, I can click on both, but I know the 90 is the one I'm actually looking for. But now it doesn't want anymore. Okay, then click on the other one, and then you see the structure recommendations. All right. And actually the plan was, if it would have worked, that you would now try to find substructures related, like for example this master motif, and then you would simply now come back to me and say, okay, maybe it's motif 214 or not. But it's always the same principle. If you have any idea what you're looking for, and especially I have to say this automated annotation guidance is really, really helpful, but only if you look for structures that you think are in any database. If you look for completely novel compounds, yeah, a reference database won't help, and the structural recommendations will also not help. So then you will still get the structural recommendations, and that does not influence how the modeling works. And you can also still use the querying to find maybe fragments you're interested in, but then you have to do it manually. And to show how this can work manually, or also with the annotation guidance, I will go now to in detail about the mode of detail plot, or tab actually. So let me go back here.
There's a question here.
Oh yeah, Nick, go on. Yeah.
Because we now have already the process resource.
Yes, exactly. Yeah, that's a good question. So I explained at the beginning there is the possibility also in the visualization app to run your file. This file is normally an MGF file, it could also be an MZML file. Best would be if it's pre-processed, MZMine, MS2LDA or so. And then you upload in the tool your MGF file, run the tool, and then it will automatically generate a JSON or JSON zipped file. And this can then be used for the visualization app. You can also run it on your laptop or a colleague and then upload it as we do it to the server or so on, if it's not that overcrowded, of course. Okay. So what I wanted to show with this exercise actually is how you would kind of process the data. I think you could just see it a little bit on my screen now, but I encourage you to try it again at home maybe, or during the conference. And then you can easily spot, okay, maybe those are fragments I'm interested in. What is also nice about the structure recommendation, if you know my substructure should be known somehow, and they align very well, then it's a good indication that the structure is actually well annotated as well. If they don't line up at all, that can also happen, then this could mean, okay, maybe this master motif is not really representing anything, any substructure. There are a lot of fragments who are not really correlating, but they need to put in some master motif, that's the modeling approach, and therefore not all 215 selected master motifs represent a real substructure. But with this annotation guidance, you can easily filter them out. You don't need to spend hours to check, does this make sense or not, if known. Okay, if you managed somehow to go to this motif details tab, then the first thing would be also to scroll down a little bit. And the first thing you can see there is another plot. It's a mirror plot. What can you see in this mirror plot? So let me start with the plot on the bottom. What you can see here, if that's a little bit too small, is you see a bunch of fragments in blue and a bunch of losses in orange. And this is actually what directly comes out of the model. So the model says all those losses and fragments are somehow related to each other. For me, when I work with my pesticides, way more interesting is actually the plot on the top. Because the plot on the top, that is also related to the automated annotation. All those fragments, they are out of the modeling results that are shared by all the structures recommended, are shown in the so-called optimized plot. And here you can see, okay, those three structures with this, I don't remember what structure, sulfuria, I think, substructure. They have four structures, 4 fragments in common, and I would say this is a really good indication that the substructure is also really accurate. I mean, if you, for example, want to check for the substructure in your data set, then you have the chance to use 4 fragments which are a good indication that this structure is really present. Because some substructures, they can also be only identified by obviously 1 fragment if it's a small substructure, but this is obviously not as distinctive as if you have 4, for example. It can also happen that there are no fragments. It simply means that the annotation before the spectra behind the structures are just not aligning. Again, can be an indication that you have to deal with novel compounds, so you have to investigate it yourself, or that the master motif is not representing anything in particular really well. Okay, then if you are somehow on the web page of the motif details, you could scroll down, and then I would try to get your attention to the table at the bottom, and there you can basically see what is in the plot, right? So you have all the fragments and losses listed, and their probability, importance, intensity, however you want to call it. This importance, if you really now want to investigate how does my master motif look like, so this is also all based on the old version, so if you're familiar with the old version, you should also be easily dealing with the new version. You can just filter. You can say, okay, give me only all the fragments that have a higher probability than X, 0.05. And then you can really have a look, okay, does it make sense from my chemical knowledge or not? And there's a slider, right, as I just mentioned. The other 2 sliders I will explain in a second, but first I want to show another, I think, really interesting plot to really deeply analyze your results. And therefore, you scroll down a little bit, and this is a bar plot. And the bar plot shows you how frequent are losses and fragments from the master motif in your in the 37 spectra, right? Remember the 37 spectra by the degree, those are the spectra with the highest association with this master motif. And you can see in this case, for example, fragment 83 has the highest association, and is more than 20 times present in the 37 spectra. Obviously, I said at the beginning that you could also see it with the average probability score. Not every spectra that has this master motif as like the best master motif is a good match. So maybe you want to filter that out as well. And therefore, you need to go back, and therefore you can use those sliders. This is again the motif probability and the overlap score, as with the motif ranking page. But here you don't do it on the average score. You can filter out the spectra based on their unique probability score. So here you can set the values really high, right? Feel free to set it to 0.5, 0.7. Just play around with it if you use it. And then you can recheck actually the bar plot, how it changes. And what you will see for some motifs that they will more or less align with the optimized fragments. All right. Then this is really, really long tab and then page. And nearly the last one, last information you can get out of the master motif, which is I think really interesting for having then a deeper look again in the spectra used as an input, is the spectra and motif section. And what you can see here, first you can find some metadata about the input spectra. So let's say you have your tomato spiked dataset, and then you can see now all spectra that are related, so there's an original spectra related with this master motif. You get some metadata from it, the scan number, okay, maybe not too important, maybe. Then the precursor, so you know, okay, I have this precursor ion that is related and overlaps with this master motif. I get the retention time, then you get again like the overlap score, document probability, and here you can see on the first page right there, really, really high, the document topic probabilities, they're all above 0.93. And the overlap scores in general a bit lower. So there, again, the sliders from the page before, they can be used to filter them out as well. I think really helpful as well is to have a look at the spectra. This is, for example, one spectrum. And here you can see how this actually overlaps with the master motif. That's not the optimized master motif, but the normal master motif. That can sometimes feel a little bit like, let's say, a perfect fit, just because maybe some fragments are really unique, but they're not representative for all of, for the entire substructure, but for the entire compound. So they will probably still be related to the substructure in some way. Yeah. So the next task I think I will basically do on my own again is the one to find actually some precursor MZs, tell me the optimized fragments, and yeah, maybe check the counts, how often those fragments are present in the bar plot for the three master motifs we just in the exercise before explored. That would have been the goal actually now. Okay. Maybe I can do it by myself and show you then how this should look like. Duplicate. Are there, by the way, are there any questions, right? You can just ask. Okay, if not, then let's move on. All right. Okay, so let me go back maybe for you. I type again just like one of the master motifs, right? Let's go maybe 124 is one. I think you haven't seen this one. Okay, it's not this one. Let's go back to the 90. So I know this. I don't know why, but sometimes it doesn't want to click. Okay. Let's go to the 214 then instead. Then we would go down, right? We can see here's actually only one common fragment, which is the 141. So therefore, I want to have the 90. Now it works. Perfect. Okay, so 90, this is a better one, but a really similar substructure. We see the recommendations, they're all the same, right? So I think it's well represented. Now we see two common fragments. Let me make them a little bit bigger. Right, there's 100, you can see 141 and 158, which are represented for the substructure. And you also, in this case, you see a lot of really large fragments, right? They're probably somehow related to something like precursor or some maybe isotopes or so on. But they're not really presented for the substructure itself, so they're not in the optimized master motive, which can be a good indication for you to just ignore them if you want to refine your substructure in the end. Okay, let's go down here. As I said, you can see again the fragments listed, ordered after the probability. And the first task would now to tell me, okay, based on the optimized fragments, how often do they occur in your data set? So you have, for example, for 141, you have it 7 times in your data set. For 158, you have it 8 times. And we can also play around a little bit with the probability score, for example. Let's come a little bit higher. And then you will see, okay, that changed a bit, right? So you have now 141, obviously present in less ones, so in 4. And the 158 is gone. Should also be somewhere. I can't see it now. Yeah. So then the second task I had in mind was actually that you now have a look. Okay, I have now, let's go back maybe here. Have a look at all the spectra you have as an input, right? So, and tell me what compounds would you expect. So for example, you have a really, really high topic probability score for the first master motive, for the first spectra for the master motive. If you scroll down, you can see, okay, this master motive has also 2 overlapping fragments, and a loss is also common with the master motive. And if you would have told me now, okay, I have those and those precursors, does that make sense? I have here a list of all the spiked compounds. And then that was 311. And we are really close, yeah. And you can see 311, there is, okay, can't zoom in. This is, represents this structure, the difluorbenzeron, and it has exactly the substructure. We could also do this for other examples in principle. I mean, that was the idea, but I think also in terms of time, I will move on. And maybe, yeah, again, right? It's a little bit of pity that it didn't work out as you maybe might have wanted to, but play around with it during the workshop if you have better internet. Okay, so I will go now through all the other types. Some of them are, I would say, more interesting, some are less interesting. The spectra search, my personal opinion, is a little bit less interesting, but what you can do there is this has all the spectra used as an input represented, and you can just search for the fragments. You can type in fragment 141, for example, and it will list all the spectra that have this fragment present. Use it for whatever you like. I mean, I personally don't use it too much, to be honest, because there are, I think, different ways to do this.
So these are your own uploaded spectra?
Yes, so in this JSON file, right, all the spectra are stored, and then, yeah, from your analysis. I think really interesting tab is the view network. So this is similar to molecular networking, but we don't do any annotation with it. But what you can see here is we have different kind of nodes. In this case, blue nodes represent a master motive, and all the green nodes are fragments. You can also add losses. I think this is then yellow, but for simplicity, we just have like the fragments, and most commonly are also actually fragments instead of losses, I have to say, because those are also only the fragments that are optimized so that are shared among the annotation, because otherwise it will be like a really, really big hairball. But yeah, the task here would be actually to first find this network, and we can then have a look, okay, what does this network represent? And in this case, right, we have 3 different substructures represented. I would say maybe the left one looks a little bit weird, but maybe that's like a methylbenzene. It's also has only one link to a fragment, and then we have a few more on the side, right? And you can really see, okay, maybe what is shared is actually the benzene ring and something like this. I think this actually takes anyways really long, even on, not long, but if you have a weak laptop, then sometimes the network generation can take a while, which means like 30 seconds, I would say. Not patient, but yeah. What you can find in this network in particular is, for example, you can find a big network that shares phosphate groups, the one with the 237, for example, with this sulfururea, sorry, in the middle, and you can also find sulfonate groups that are linked together. And this is just also, again, right, for exploring your data set. You don't know what you're looking at, what is linked together, and also some expert knowledge, if you have some, that could also be really helpful to extend it. One also important thing I want to mention is, if you're used to using Cytoscape, for example, you can, when running the tool, a GraphML file will be generated, so you can just use it and put it into Cytoscape. And also, I will mention it later, but in a case study, we also used it and together with MolNet Enhancer to have a combined network of Spectra as well. Let's move on to the last step, which is called motive search. And that's also a really interesting one. Actually, there I will address something in a second where you can actually help us. And the motive search has the goal to use the knowledge acquired from the users. And that was normally done with MotiveDB. We still have MotiveDB. It's a little bit different format now, but I think no one was anyways exposed to it. And here all the motive sets that were manually annotated a long time ago, maybe 7 years ago. And you can select them, right? I just selected one of them, the GMPS. So MS2LDA was a long time ago run on GMPS. And then 77 motives were manually annotated. You compute now the similarities between those 77 master motives manually annotated with the automated annotations made by the new version. And then you would see again like a long table, and with like a similarity score between the master motives generated automatically and manually. And you see, for example, the first one has a similarity score of 98, the second one 93, and they have an annotation which was in the earlier way always in a descriptive manner. So it would say this fragment indicates a methylbenzene, or for the second one, okay, fragment I indicated for conjugation of a phosphate group. In the new version, again, right, it's now smiles. You can still add them manually if you want. But yeah, have a look. So the second one says it's a phosphate group. Then we can click on a master motive, and we can see, okay, also the automated annotation has, I would say, high certainty, okay, it's somehow related to a phosphate group. And we also did some benchmarking it, and it seems like it aligns actually really well with the manual annotation. So if you were relying earlier when using, for example, MS2LDA on the manual annotations, this will work quite well for you as well. Yeah. Now actually the goal, I mean, far away from that, but was to just that you explore this a little bit and maybe find some annotations that do not fit, where the manual annotation does not fit the automated annotation. There are some, that's not a trick question to show how well it works. There are some where it doesn't align, and sometimes it can be really interesting because then you see the limitation of the tool, right? Of course I want to sell the tool a little bit, but I also want you to use it in a manner that you will maybe find it when you're at home or in the lab, right? If I show you only the good examples and then you see like, oh, it doesn't work like that, then yeah, also not what I want to. But in general, it aligns quite well. If it doesn't align, then again, look into the motive details, what fragments are important. It can sometimes be that you have to increase the number of master motives in the modeling or decrease, it depends. Because if you have only a really small number of master motives, it can be that several substructures are merged into one master motive and then the annotation doesn't work that well anymore. Okay, I think since we didn't do any of the workshop stuff actually together, I think we're good in time, and I just want to show you 2 examples how we used it and what you can actually do with it. So in the manuscript, we just published in a bioarchive. Rosina, my colleague, used a fungicide dataset, and she used MS2LDA on it and was able to detect substructures within the erinacine family. In the paper published earlier, you could see that there was a network built with GMPS, and all the blue lines or edges and the green ones, they are represented by the actual substructure, or they have that in common. This graph or network was generated with molded enhancer, so it's actually really, really simple with maybe, I think, some Python skills to build your own molded enhancer workflow in principle. One thing that is a little bit closer to my heart, again, is to use MS2LDA for pesticides. And there I will talk also about a feature I didn't say yet, because this is only if you use it in a notebook, for example, and it's currently not available in the visualization app. So what MS2LDA does is it generates all those master motives, right? So you have a bunch of structure recommendations. And one thing structures can be represented with are fingerprints, chemical fingerprints. If you are somehow familiar with cheminformatics or not, then a fingerprint is a binary, often binary representation of if certain structural features are present in a molecule or not. For example, it could be you have 160 bits, so that's either 1 or 0. And if there's a benzene, then at one position it gets a 1. If there's not a benzene, then you have to have a 0. That's a representation of structures within a computer-readable kind of type, let's say it like this. And we calculate fingerprints for the substructure. So we see where do all the fingerprints from the structure recommendation overlap. And this is our suspected substructure fingerprint. And then what I did is I trained a machine learning model. This is not much you need to do. I used a TOX21 dataset, and probably it's like 10 lines of code, maybe even less. Then you need 3 lines of code to load it and predict with this tool the fingerprints. And then, because again, food safety, right, I maybe want to prioritize certain substructures based on their toxicity. So I have all the predictions, and then with another 4 lines of code, I can now prioritize my compounds based on if they are toxic, and I also filtered that I want to have 2 fragments at least. And then I get a list. I get here a long list of compounds. It's not too long. It's maybe 20 values. And when I have a closer look, then you probably see something we're familiar with, master motive 90 and 98. And those are related to those 2 pesticide classes. And that's a quick way, with not a lot of experience for programming needed, that you can build your own workflows of that, right? So very happy to talk about that if you're interested in those workflows. I'm working on that myself, so feel free to ask me anytime. All right, coming to an end. If you have any further questions, we have 2 posters If you're more interested in the natural product side, please go to Rosina. If you're interested in food safety, feel free to come to my poster. If you have any question about MS2LDA, just ask either of us or Esteban as well. I think actually everyone who has like Wageningen in their poster, just ask them. They can at least refer you to us. And then the last slide is then just a thank you. So we were helped a lot for the server and visualization app. I shouldn't mention server now, but with the visualization app by Joe Wendy, who was a former collaborator as well, and helped also here quite a lot, obviously also for the workshop, Justin, Esteban, and Nick. And also our bioinformatics group. If you haven't done yet, there are some QR codes for the visualization app. And for the GitHub repository, feel free to take a screenshot or scan it. And otherwise, that's it from the workshop. I think we're a little bit early, but I still allow questions of it, obviously. Yeah, please. Yes.
I was wondering, because I know MS2LDA is integrated into some other tools, for instance, on the GMPS platform.
Okay, perfect.
Thank you. Julie from Athens in Greece. From what I remember, MS2LDA is still integrated in other platforms like GNPS and the MolNet Enhancer.
Yes.
Stuff, right? Can you tell us about this? Is it the latest version? How is it basically integrated in it? Thanks.
Yeah. So currently it's not integrated in GMPS. In GMPS, it's I think still the old version if it's running. But it's not a new version. I think, therefore, we have to talk with the people from GMPS, and then we can make that running. I'm not sure about any timeline, but we had some conversations with them, with me personally, but that would be an idea to upgrade that, yeah.
Okay, so the version there is one version available now, but it's an older version, that's what you're saying? Or it's not available at all?
Is GMPS running MS2LDA currently still?
In GMPS 1, thanks, it did, and maybe it still does. In 2, we did some initial attempts, but I don't know the latest, because they're still developing GMPS 2 as well. So it's very hard to, it's all work in progress. But there are some people who are heavily involved in GMPS 2 in the audience, so maybe they can comment on that.
Yeah.
Thank you.
But there's definitely an option that we will collaborate with them to make it running in the new version. Yep. Anyone else? Any other questions about anything?
Yeah, so whilst you're thinking about questions, so maybe it's good to realize one thing we changed now is that on the server you can no longer run jobs. But yeah, you can still visualize the results coming out of the jobs. And the idea is then now that, first of all, everybody can install the visualization app locally. You can run your own data locally. So there's no kind of privacy issues with the data there. And second of all, the server that we have been running almost for 8-9 years. We set up in a way that people could upload their data after running on GMPS or directly running it on the server. But we realized that, over time it kept growing and growing and growing, and that also run out of control, right? So that's also a reason why we changed that. So now, and as a side effect, nice side effect, it will be also much easier to share your results with others, because the generated visualization files are not that large. I mean, the case study file here that you used was 17 MB, and maybe if you have a bit more data, it will be like 50 MB. But you can easily share that as a supporting information with your paper. Other people can upload that file into the app and explore and browse the results as well. So that is kind of the philosophy now. And we hope that you will all keep enjoying to use the tool.
Yes. Are there now any further questions? Otherwise, just come to the poster if you're interested, and yeah, talk to us.
Maybe another thing then to mention, right? Because if it wasn't clear yet, so who knows what is MassQL? All right, so that is, well, 1/5 of you. So MassQL is a pattern, it is like a mass spectral query language that you can use to search for patterns in the mass spec data. And there was a paper that came out a few months ago that you can check to know all the details. But what we did is that we changed that language a little bit so it can work with the motives, right? So it was some effort, but now it's working. And it means that you can very flexibly search through all your motives depending on the fragments, losses, but also the metadata that comes with motives, like the positive mode, negative mode, also the sample types, etc. So for those of you familiar with MotiveDB, you are asked to put in a set of kind of detailed information on the metadata with the motive set. So whether it comes from plants or urine or standards and things like that. So you can also use that in your queries. So meaning that you are much more flexible now in finding the exact motives that you are looking for. So I think it's also good to highlight that. But yeah, now I hope we still have a few questions. And if not, then I want to personally thank Esteban, Rosina, Jonas for all their hard work. So and I hope that for those of you that got it to work, you'll get a chance later this week to play with it a little further. And for those of you that are still working on getting it installed, I hope you will find better internet than here and get it to work.
Yep. Yeah, thank you. Have a nice conference.